Alright, welcome back. This is Chapter 6, Part 3, and now we're going to talk about electron configurations of the atoms. Okay, so an electron configuration of the atoms just tells us the way electrons of an atom are distributed among the orbitals. Okay, for example, we can look at lithium, okay, which is in period 2 of group 1a. So we write out all the orbitals that have an electron. Okay, so we have the 1s orbital, we have the 2s orbital, and we show how many of electrons are available. So the 1 just refers to the energy level, the s is the type of orbital, and the number of electrons in that orbital is 2. Okay, so thus the first energy level has 2 electrons, the second energy level has only 1 electron. Okay, and we'll discuss that more in a minute. Now, one of the other things we can do is we can depict these electron configurations using what's termed an orbital diagram. Okay, and this orbital diagram is basically we draw out some boxes and draw in our electrons with these upside down arrows. Okay, so each orbital is represented by a box. So here's the 1s orbital represented by a box. The 2s orbital is also represented by a box. And then we put these half arrows in for each electron. Okay, so 1s has 2 electrons, so we have 1 up and 1 down because they have to have opposite spins, right? Same thing with the 2s, we only have 1 electron, so we can either draw that up or down. Alright, so we can actually easily determine the electron configuration by using the periodic table of the elements. So electrons are going to be filled according to each element, and we just start at the beginning here, and we can just move through. Okay, and we'll take a look at that more in just a minute. So in this figure, you can kind of see that I've labeled the different groups of the periodic table. So we have the s, we have the d's, we have the p orbitals, we have the f orbitals. Okay, and so when trying to figure out the electron configuration, you can actually use this figure to really remember which orbitals are filled and in which order. Okay, for example, if we determine the electron configuration of iron, right? Iron here, Fe. Okay, in order to write out this electron configuration, we can basically just come back and start at the beginning. Okay, and we're in the first energy shell, n equals 1. Okay, we're in the s orbital, right? So we have the 1s, and we have 2 electrons in that. Then we go to the second energy level, where now we're in the s orbital again. Okay, so we have 2 electrons in that s orbital, 2s2. And if we just keep moving across the periodic table, we see we hit the p orbitals. Okay, and here we're still in the second energy level, but we're in the p orbital. We have 6 of those, right? We're still going across. We haven't hit iron yet. And so that means that the 2p has 6 electrons. So then we just move ahead to the next. Now we're into the third energy level where we have 2 electrons. We still haven't hit iron, so we have 2 electrons there. We go across and we've hit the p orbitals again, and so now we have 6 electrons in the 3p orbital as well. Alright, so we continue to move across. We come down to the 4th energy level. Well, we still haven't hit iron, and we have 2 electrons, 2 more, right? So each one of these gets an electron. And then we move across and we see, okay, wait, now we're in the d orbitals. Okay, when we hit the d orbitals, the one thing to note is that now this is no longer the 4th energy level. When we hit d, we're taking the energy level minus 1. Okay, so this is actually the 3rd, okay, of the 3d orbital. Okay, and then this would be the 4th d orbital, the 5th d orbital, the 6th d orbital. And when we go to the s, we actually subtract 2 from this number of the energy level from here. Okay, so this is actually the 4f, and this is the 5f orbital. So if we come back, we just filled the 4s2 orbital. Now we're into the 3d orbital, and if we go across here, we have 1, 2, 3, 4, 5, 6 electrons before we hit iron. Okay, so that means the 3d orbital only has 6 electrons, which takes us to iron. And so our entire electron configuration for this is if we write out each of these: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay, that tells us we're at iron. Alright, so now we can kind of turn to what's termed Hund's rule. Okay, and Hund's rule is very important, and it basically says that the lowest energy is attained when the number of electrons having the same spin is maximized in what's termed degenerate orbitals, or orbitals with the same energy. Okay, so if we just look at the first 2 here in this table, lithium and beryllium, we see that the 1s is both filled, right? The 2s for lithium has just 1 electron. The beryllium has 2 electrons. Okay, and so the lowest energy is attained when the number of electrons having the same spin is maximized. So here we have electrons with opposite spin. Here we have them the same. Okay. All right. So we just talked about the electron configuration of iron. Okay, and you saw how long that is. And if we go even further, you'd have this really long electron configuration written out. It'd take you forever to do it. And so what we do is we write out what's termed the condensed electron configuration. Okay, but to do so, we really need to understand the difference between what's called core electrons and valence electrons. So core electrons just refer to that inner shell electrons of an atom. Okay, and these core electrons can be represented by bracketing the symbol of the noble gas that precedes the element in question. Okay, the valence electrons are just those outer shell electrons. These are the electrons that are gained or lost during a chemical reaction. So let's go back briefly and look at iron. Okay, so the core electrons is everything preceding the last noble gas. Okay, so if we go backwards, okay, now we're at the 4, so we go up 1. Well, our noble gases are group 8A, right? And the last noble gas was argon. And so in order to write the electron configuration of iron, we could just put argon in brackets and then start down on the next level, which is our valence electrons in that outermost shell. And here we see we're in N equals 4, 4s2 is filled. And then we come back and here we have the 3 orbital, right? The third energy level, 3d6, okay? So if we come back to the condensed electron configuration, we will write in argon in brackets, and then we'd write 4s2, 3d6, okay? A lot simpler, a lot easier. Okay, so we can do this for all atoms. The last thing of this part 3 is basically there are some irregularities that occur when there are enough electrons to have filled both the s and d orbitals, okay, on a given row. So there are some other irregularities that you should read about in the textbook. I'm not going to go into them here, but you should know about them. And really the one I'm really concerned about is the electron configuration of like copper would be just argon 4s1 3d5, right? So here's copper, right? And so basically it's 4s1 3d5 rather than what you would expect, which would be 4s2 3d4. Okay. All right. So that concludes the chapter 6. This was part 3. At this point, we're done with chapter 6. Good luck.